James Peebles is one of the world's foremost cosmologists. For over 40 years, his research and foresight have helped to transform cosmology into a focused and rapidly advancing science. Peebles laid the foundation for many modern cosmological investigations by predicting the existence of cosmic background radiation, popularizing the notion of dark matter in the universe, and developing a theory of how the universe evolved into galaxies. He also pioneered statistical tests to track and quantify the motions of matter in the cosmos. These tests necessitated the creation of new computer-based simulations to compare the competing theoretical models of Peebles and others. Peebles continues to study the related issues of cosmological tests, the nature of dark matter, and the origin of the galaxies. Peebles received his BS in 1958 from the University of Manitoba and his PhD in physics from Princeton University in 1962. And after spending 3 years as a postdoctoral fellow, he joined the faculty of the Princeton Physics Department. Peebles joined the physics department where he's remained throughout his career. In 1984, he became the Albert Einstein Professor of Science at Princeton. Peebles retired from teaching in 2000 and continues to research the workings of the universe as an emeritus professor. Peebles' profound contributions to astrophysics and cosmology have been recognized with numerous honors, including the Shaw Prize in Astronomy, the Cosmology Prize of the Peter Gruber Foundation, the Gold Medal of the Royal Astronomical Society, and the Jansky Prize of the National Radio Astronomy Observatory. Please join me in welcoming Professor James Peebles.
Thank you. A true pleasure to be here, a place that I've always enjoyed visiting. If you are of a certain age, the odds are you're recalling the stir caused by the release of the first images of planet Earth from outer space. A little surprising, perhaps, that people should be stirred by it. We knew then that the Earth is round, the clouds are white, the oceans are blue. Yet knowing is different from seeing, and the experience of seeing the planet Earth had a big effect, I think, on our appreciation of the fact that we live on a definitely finite island universe, and that it behooves us to take a little bit better care of it. So I propose to use the tendency of so many of us to be fascinated by images as a vehicle in describing to you what we know about the universe in the large. So let's get to work and remind ourselves that the next planet out, Mars, is not as photogenic as planet Earth, but certainly is a fascinating object. We know that, for example, by the work of Percival Lowell. I introduce him because he'll play an important part later in my story this afternoon. Perhaps you know the verse, "Now we are in Boston, the home of the bean and the cod, where the Lowells speak only to Cabots, and the Cabots speak only to God." This Percival was a Cabot. He augmented his personal fortune by work in the financial markets, then indulged in his great interest in many things, first the Far East, then astronomy. He's honored by astronomers for his decision to place his observatory in an excellent site in Arizona and to hire first-rate astronomers to build instruments for it and use it. Led to capital discoveries, one of which I'll be mentioning later. He tended to get a little over-interested in Mars. He thought he could see all kinds of things on it. In fact, he thought he could see evidence of an active civilization shaping the planet. Well, he was a little misled, but he was right in the general notion. Surely, if you looked at Mars with a little care, you'd see fascinating new things. And indeed, here is a close-up image of the surface of Mars, a river, long since dried up. But won't it be fascinating when we have a view of what's left on the sides of this old river? The next planet out, Jupiter, has the composition of the Sun, about 3/4 hydrogen, 1/4 helium, and trace amounts of the stuff out of which Mars and the Earth are made. It has weather. The Great Red Spot has been there for a couple of hundred years. a tropical storm of the sort you see on the Weather Channel. Now, we're not alone in our solar system. Here is a tribute to Professor Sarah Lee Lippincott, based not far from Princeton, an authority from the last generation of the nearby stars. And here the model she made showing the relative positions of these stars, their relative sizes and colors. To my deep regret, I missed the chance to take a photograph of this model. But we have a new generation that are adept with computers, and they show us this picture of the relative distributions of the nearby stars. Here's the sun. The relative sizes are in proportion, the relative positions in proportion, but of course the sizes of the stars greatly magnified. You see that there are stars bigger than the sun. Sirius here has twice the mass of the sun, and it's kind of hotter. It has a companion that's quite faint but very massive, a white dwarf, the remnant of an exploding star that's lost most of its nuclear fuel. You notice that most of the stars are less massive than the sun, redder, a lot less luminous. On a star-by-star basis, the sun is pretty big. The grid you may be able to see is kind of cute. For example, I can go to the right along the plane of the board, go into the board and down, and I get Epsilon Eridani, which attracts our attention a little bit because, according to a local expert, carrying on from Professor Sarah Lee Lippincott, Jeff Marcy on the left assures us that that star I was just pointing to very likely has a real planet, another Jupiter, another solar system. We're not alone. There are other planetary systems. It's going to be fun to explore them. Some stars reach the end of their supply of nuclear fuel in the age of the universe, explode. This is one mode of explosion. It just blows itself apart in the supernova. It scatters about the products of the nuclear burning of fuel to make energy to shine, to radiate starlight. This nuclear waste collects in clouds and makes the clouds of hydrogen mostly, polluted heavily with grains. The grains make the clouds dark. New stars form out of these gas clouds. You can see that in this example, the bright young stars are on the far side of the cloud. You can see the light from the stars glinting off the gas clouds, but you can't see the stars directly. There's too much dust. It blocks out the starlight. That's an important effect in looking at our galaxy of stars as a whole. Here's a picture of the whole sky. Many photographs taken at night always, of course, as we move around the sun. And then the results stitched together to make a map of the whole sky, distorted on the edges greatly, of course, because we're taking a sphere and projecting it onto a plane. But you can get the general idea, a band of light running across the sky, the Milky Way. You see rifts running through the band. That's not absence of stars, but rather presence of this absorbing dust. And what we are seeing is that we live in a disk of stars. There are stars out of the disk, but most of them are in this disk, and we're seeing the integrated light of the stars running across the sky from this disk of stars. It looks from this picture as if we're close to the center of the disk because there are about as many stars in each direction seen. But that's an artifact of the absorption by dust. This is a better image of where we are in our galaxy. Again, an all-sky picture, but now taken at wavelengths slightly longer than what we can see. At longer wavelengths, the dust is much less absorbing, and so we get a much clearer picture of where the stars are in this Milky Way galaxy. You see several important things. You see the disk of stars. You see a bulge near the center of old stars. And then you see that we are distinctly in the suburbs of this island universe. We are not alone. There are other galaxies of stars. Here's one very much like our Milky Way galaxy. You see a bulge of old stars, a disk of stars. You see rifts running through the disk. That's gas again, polluted by heavy elements that blocks the starlight. There are several varieties of these galaxies of stars. Here is another one with a much bigger bulge of old stars and just a trace of relatively young stars, gas and dust in this disk. A beautiful image, from the Hubble Space Telescope, a magnificent instrument whose existence depends these days upon support from people like you who let their Congress people know that it would be ridiculous to turn off this magnificent instrument that gives us such gorgeous images of the world around us. I hope you agree. Don't applaud me, applaud your Congress people. Other galaxies have no disk, they're all bulge. These galaxies don't sit in isolation, they tend to appear in groups. On the left you see a picture of 3 galaxies. It's a negative, so where there is starlight, it's dark. A big disk, and then 2 smaller and more irregularly shaped galaxies. There's a lot of hydrogen in this concentration of galaxies. The hydrogen emits radio radiation at 21 centimeters wavelength. A radio telescope can detect that radiation and give us a picture of this system at a different wavelength, giving us a different impression. If you had eyes sensitive to 21 centimeters, and you had very good eyes, you would see the right-hand image, and you would ask yourself, now wait, is this one galaxy? Notice the swirl of spiral arms running from one to the other. The definition galaxy is a touch arbitrary, I would submit. You see another example of that in the next image. Here is a plot of the galaxies in one region of the sky and at one range of distances from us. You notice a tight concentration of galaxies in the center and then dribbling off to lower and lower densities. It's just like the distribution of stars in that galaxy I showed you that is all bulge. A cusp in the center and then the distribution flaring out on the sides. It's a galaxy of galaxies, which is neat. Here is a picture of that galaxy of galaxies. It's dead in the center of this plot. This shows the distribution across about 100 degrees of the sky, looking up away from the disk of our galaxy where obscuration by dust is not too important, showing you the texture of our universe. That's the large-scale nature of our universe. Here is the astronomer, Donald Shane, who took the data to make that image. These are then graduate students, Jim Fry, Ray Siniera, Mike Selder, and Bernie was off screen. Maybe he wasn't even in my office when this photograph was taken, who took Donald Shane's data and turned them into a map. Shane, with his colleague Carl Wirtanen, counted the galaxies one by one with a traveling microscope in the 1950s. It took them a decade, one by one, with a traveling microscope, picking out the galaxies, making a pile of data sheets, shown here. This is a set of copies in my office. Think of them. Think of the effort. And then think of the fact that in those days, there's not a lot you can do with 1 million numbers. High-speed computers came along. We could take his data, which was taken with such care, that we could make this image and show it to him and asked him, so is this what you are seeing? And have the pleasure of him laughing at us and saying, I was looking at this one galaxy at a time. This is the texture of our universe in the large, but we can go to bigger scales. Let's not hesitate to step back another step. Oh, I should have remembered to tell you that, of course, data improves. This is a modern version of what you've just seen, called the two-mass survey. Tom Jarrett and colleagues, again, photographed the whole sky, but now use computers to identify the galaxies and plot them up. It's at about the same limiting distance, and you see the same texture. This is the texture of our universe. You see running through this image of the whole sky a darkish band. That's dust in our galaxy, and in this projection of the whole sky, the plane of the Milky Way is running in this S-shaped curve. You should ignore that, and you should trust the rest. This is the way we look. But let's look at still further. Let's look on a still larger scale, and we can do that by noticing that some galaxies, such as this one, have in the center, in fact all the big galaxies have in their center, a massive compact object that the odds are very strong is a big black hole. The main operative thing about a big black hole is the strong gravity as you get close, and it tends to squeeze things as they fall in. It makes an explosion of this sort. that is the center of that galaxy, and this Hubble Space Telescope image shows you a lovely jet of light running away from the center. What's happening, in very rough terms, is illustrated by the consideration, what happens if you take a tube of toothpaste in your hand and hold it firmly, and then you're startled, very much startled. You squeeze impulsively that tube of toothpaste, and you make a jet. Where is it? Here it is, an experimental demonstration of a jet produced by compacting, strongly compressing material. In galaxies, this compression is sometimes so violent that it makes a jet of material that is very much bigger than the galaxy, and that it produces radio radiation. Here, an image from the very large array in Socorro, New Mexico, an array of radio telescopes with superb image-making qualities. Isn't it a delight to see this? Eyes that are as big as, well, a couple of miles across. Sensitive to light, 7 centimeters wavelength. And what do you see? A jet running on one side, alternately, I think, one side or the other. Great blobs of plasma, wisps of dense plasma nearby, and hot spots on the end. A really wonderful thing. An exploding galaxy left us this marker. This doesn't happen very often in galaxies, and when it happens, it can be seen at great distance. And so by mapping up the distribution of these galaxies, we can get a really large-scale picture of what's going on in the universe. And this is what you see. This is a distribution across half the sky of those exploding galaxies, the brightest, the nearest 20,000 or so, give or take. Now, you should be careful. The hole in the center is just, the instrument couldn't point up there. And the hole down here, in interference by the sun. The plane of the Milky Way in this map runs along here like so. This is a very bright source in the Milky Way. It's not another galaxy, but it's bright enough to confuse the instrument. So you should ignore, please, this region. You should ignore the concentrations of sources along here. And ask yourself, what do you see? Well, it's even duller than Mars. You don't see anything. And isn't that a remarkable thing? You pause to consider that in physical science we study sections from a hierarchy of structures. There are cells that contain atoms. The cells are made into, well, arms and legs. Arms and legs are made into people who are made into communities that live on the planet Earth, that's part of the solar system, that's part of the galaxy, that is part of a supercluster of galaxies. Level upon level of structure, and then it stops. Isn't that remarkable? And of course, this remarkable fact is what makes it possible for us to say we're making a theory of the structure of the universe. We're not just taking a section of a hierarchy of things within things within things. We've come to the end of the hierarchy. And we can study the behavior of this end of the hierarchy because, as you see, it's wonderfully simple. Quite an advance, quite a conceptual advance to see the end of structure. You understand that within this map there is all that clustering of things that you've seen illustrated earlier. But because the objects here are so rare and we are looking over such a range of distances, we lose all that clustering. We see only the large-scale pattern, and what we see is uniformity. That is the first law of cosmology. Let's go on to the second law. Oh no, I forgot to say, it's fun to look at the telescopes that produce some of these images. This is a great 300-foot telescope in West Virginia on which those data were taken. And this is the great 300-foot telescope in West Virginia as the project was completed. It fell down. It's all right. No one was hurt. And the senior senator from West Virginia was not about to see the great state of West Virginia lose a major scientific instrument, and so somehow funds were found to build this elegant, new, much more powerful Robert C. Byrd Green Bank telescope based in West Virginia. I don't quite know what to think of this, but I come up with the conclusion that it's only pork if you're not at the trough. It's a magnificent instrument for science. How can I complain? As a taxpayer. There it is now. To emphasize it, we have something simple that even a scientist can deal with. And I come back to Percival Lowell, who, as I said, earned the deep respect of astronomers by his decision to do great science by hiring great astronomers to do it. One of them, Slipher, built the instrument and used it to detect the spectrum of light, intensity of light at each wavelength coming from a galaxy, showing first that the light from galaxies is just starlight, a bunch of stars, and second, that in distant galaxies the light is shifted toward the red. The effect proposed then, and now we know to be the case, is the Doppler shift, which you're all familiar with if you stood by the side of the road and noticed the noise coming from a passing car. The noise of the motor says, boom. The pitch of the motor isn't changing as the car roars by, but as the car is approaching you, the wavelength of light is pushed together. That makes the pitch go up. As the car is moving away from you, the motion stretches the wavelength, the pitch goes down. Boom. So it is with light. Slipher, demonstrated that the light from distant galaxies is shifted toward the red as if they were moving away from us. We now interpret that, I believe entirely correctly, as the effect of the expansion of this uniform universe. It was a deep puzzle at the time he found it, and this person, Georges Lemaitre, Belgian, in 1923, shown here, a few years later, gave the now accepted explanation, the expanding universe. In this year, he discovered not only a great love of God, he's Roman Catholic, but also of general relativity theory, the theory Einstein had invented for a better theory of gravity, one that is now very thoroughly tested. In those days, it was just a theory, but people were looking very hard for applications, and Lemaitre found one. Here are some key players in the next part of the story. Einstein, as I said, invented general relativity theory that Lemaitre was soon to use. This person, Dutch, Willem de Sitter, will appear in a moment, but try to remember his face. The hair has moved from here to here. And finally, the professor of astronomy at Cambridge University in England, Arthur Stanley Eddington. Lemaitre decided to expand his knowledge of general relativity by studying first at Cambridge, and here we have evidence of it from a letter from Eddington. I certify that Abbé Georges Lemaitre has been attending my lectures and pursuing his studies and investigations to my entire satisfaction during the academic year 1923-1924. From there, Lemaitre went to MIT, the other Cambridge, Massachusetts, where he continued his studies in general relativity theory, and he attended a talk by this astronomer, Edwin Hubble. I'll talk later today and again tomorrow about this instrument and about this person, Richard Tolman. He heard from Hubble about Hubble's studies of Slipher's effect and about the curious pattern that Hubble was finding, that the more distant the galaxy, the more rapid the redshift, the more rapid the recession velocity of the galaxy. It was that lecture by Hubble that inspired Lemaitre to invent the theory of the expanding universe. Here again, I don't remember why I showed you twice, but here is, we have evidence. So now let me tell you the story because it is somewhat educational. Lemaitre wrote his paper on the expanding universe in 1927, but he published it in a Belgian journal that the in-crowd did not read. He waited patiently for response from the in-crowd. What do you think of my idea? Got none. He wrote to Eddington, reminded him of his acquaintance and said, what do you think of my work? No response. Not until a second letter, several years later, was there a response. And it was then a very vigorous one. Eddington wrote to De Sitter. Here again is De Sitter. And here is the letter Eddington wrote to De Sitter. Here is the date, 1930. And here is an interesting message. First, Lemaitre's address in Louvain in Belgium. Then a comment. A research student, George McVitie, and I had been worrying at the problem and made considerable progress. So it was a blow to us to find it done much more completely by Lemaitre. A blow softened, as far as I am concerned, by the fact that Lemaitre was a student of mine. Well, you learn from this first that if you do something great, you will win friends. But we have to admire Eddington for his decision immediately to arrange to have Lemaitre's article reprinted in a prominent journal of astronomy. He made Lemaitre famous. You can tell he was famous because here is Dicke, a caricature, following an interview by him, published in a prominent newspaper in the Netherlands. The bottom part of the figure I will be discussing tomorrow. The top part, I hope you will agree, is a pretty good caricature of the great Professor Dr. Willem de Sitter. And here is an analog showing de Sitter's explanation to the newspaper of what Lemaitre had in mind by this notion of an expanding universe. Pretend that you live not in 3 dimensions, but in 2. Pretend that you're an ant that may crawl along the surface of this balloon. You notice it's kind of a neat arrangement. This world the ant lives in is finite. The ant may start in a given direction and move in a straight line. It'll end up back where it started from. No boundaries to this universe, no edge. It's homogeneous, uniform everywhere, but it's finite. You might ask me, so what about the space off the balloon, inside and outside? I tell you, don't ask that question. You live in 2 dimensions. You live on the surface of that balloon. One other cautionary note, stars and galaxies are more or less sketched on this balloon. The stars and galaxies aren't expanding. You have to think of those as little pieces of paper, perhaps, attached to the balloon in one spot. But now the really neat thing. You are living on one of these galaxies, and you look around, and what do you see as the balloon is blowing up? You see the nearby galaxies moving away from you, and you see further galaxies moving away from you fast. That's just the pattern that Hubble had been discovering for an expanding universe. That was a great connection that made everyone so excited in 1930. Now, of course, it's one thing to say this fits the observations, uniformity, the redshift, the apparent Doppler shift, an expanding universe, but how do I know that's the way it really is? You know that the way you test that by finding other effects, other checks, other experimental conditions that are required to fit by the same theory of an expanding universe. It was Lemaitre, in fact, who realized that there ought to be further evidence of this expanding universe theory, that if the universe did start expanding in this very different state, surely it left fossil evidence of the very different state. He writes in this photograph, this is a photograph with Einstein, he writes, the evolution of the world can be compared to a display of fireworks that has just ended. Some few red wisps, ashes and smoke. Standing on a well-chilled cinder, we see the slow fadings of the suns, and we try to recall the vanished brilliance of the origin of the worlds. Let's find the vanished brilliance. Let's find fossils of that time when the universe was so very different. The person who showed us how to interpret the fossil we have found is Richard Tolman, professor of physics at Caltech in Pasadena, who developed the theory of heat radiation in an expanding universe. Heat radiation you've all experienced. Stand by a fire and put out your hand, you're feeling radiation. That's heat radiation. It has an important property. In a closed vessel, if I keep the walls at a definite temperature and let things relax to equilibrium, then the vessel will be filled with radiation. Blackbody radiation, often called thermal radiation, with the property that you tell me the temperature and I'll tell you the intensity of that radiation at each wavelength. What Tolman shows is that in an expanding universe, this radiation doesn't go away. There's no place for it to go. But it is cooled by the expansion of the universe, and the really important thing is it maintains its thermal blackbody spectrum. And so, a fossil from this early time, if the universe was hot to begin with, would be the remnant thermal radiation, and we would know it's thermal by its spectrum. This was used after the end of the Second World War by George Gamow, a great astronomer of a previous generation, with his student Ralph Alpher, and a few others to make a theory of the origin of the elements. In fact, it is now our standard theory for the origin of helium. Most of it was cooked in the hot Big Bang. I won't get into that detail today, but just to remind you of this photograph, maybe some of you remember living under the threat of nuclear war, and this Herblock image of the hydrogen bomb, and the caption, 5 minutes, for scientist says world was created in 5 minutes. Well, that's the first 5 minutes of the expanding universe. Here is a photograph of a temporary building at MIT, built during the Second World War for war research. Here is a professor of astronomy at MIT, Ray Weiss, pointing toward this temporary building, built during the war, torn down only recently, and to my mind, a sad event. There ought to be things preserved from old times. But here is a photograph of my thesis advisor, Bob Dicke, on top of that rooftop with one of his inventions, a microwave radiometer. I'll explain now what this radiometer does. Here is a sketch of the skyline of Cambridge from that rooftop. In those days, Cambridge had factories. Some of the factories had chimneys, and some of the chimneys were warm. Up above is a chart recorder showing the response of his microwave radiometer as it was swung across the sky and swung past those chimneys. You see what's happening as the different lines are different angles down from the vertical. As the radiometer is swung across the horizon, it shows a deflection at each warm chimney. This is just the device to detect thermal radiation. This is a photograph of Bob Dicke about 25 years later. On the left, Jer Yu, my first graduate student whose role will appear in tomorrow's lecture, and David Wilkinson, a longtime friend and colleague, close colleague at Princeton University. Slightly before this photograph, Bob had the idea that one ought to look for this fossil radiation from a hot early universe. And he persuaded David Wilkinson to build a Dicke radiometer for the purpose of looking for this radiation. Here is Dave in working clothes. He's holding, if you can see, a screwdriver. Behind here is his colleague. Perhaps you can see the sleeve of his plaid shirt, Peter Roll. They built this radiometer to look for that thermal radiation that would be present if the universe started hot and expanded from a dense, hot state. Here is a telescope at Bell Labs, a mere 30 miles or so from Princeton, that was used in early experiments with satellite communication. First, bouncing signals off a big balloon in orbit back down to Earth, then later a satellite that would receive television signals from the ground, transmit them back down to the ground. Early efforts in long-range communication. This telescope had a curious problem that vexed very much Bob Wilson and Arno Penzias, who wanted to use this telescope for radio astronomy. It was detecting too much radiation. They were at their wits' end with this curious feature of this radiometer when Bernie Burke, here in the center, who knew both groups, told the two groups to get together. The one looking for the radiation, the other with the radiation but not knowing what to do with it. Bernie is at MIT. It's curious how these things happen. 1925, Lemaitre is at MIT. 1945, Bob Dicke is at MIT building a radiometer while Lemaitre's country is being torn apart by the Second World War. 1965, he is bringing at MIT the two groups together. Things work in curious ways. Here's the situation. Penzias and Wilson, at 7 centimeters wavelength, had radiation coming in from all directions equally strong that they didn't know what to do with. Here, shortly after the two groups met, the Princeton experiment was completed. It detected radiation here. This is the curve of intensity at each wavelength you would expect if this radiation is thermal, black body, left over from the early universe, if it's a fossil. And you see it already looked pretty good. The story of much of cosmology for the next several decades was the work in filling in this part of the curve and checking, does this radiation really follow the prediction you would expect if this is thermal radiation left over from the hot early universe? A lot of work was done in that direction, but I will immediately go to the experiment that solved the problem. It had to be done above the Earth's atmosphere because at radiation, at wavelengths near the peak, the atmosphere is strongly absorbing and emitting. It just totally makes the experiment impossible. You have to get above the atmosphere. Here is a proposal to NASA for a satellite that became known as COBE, Cosmic Background Explorer. The proposal was made by John Mather. Here's Dave Wilkinson. One of the PIs was Mike Hauser, who made this image I showed earlier. The other was George Smoot, who I will be roasting tomorrow. It's interesting that Mather was at the time a postdoc, and he was proposing to bet his career on a satellite whose design started in the mid-70s and was flown in 1990. Imagine it, the work required. And during that time, he was not accumulating a track record of research. He was concentrating on one big basket of eggs that could, on launch, break. He is made of stern stuff, for which he earned this year's Nobel Prize in connection with another person who will be discussed tomorrow. Here is a photograph of the COBE group. Here you see George Smoot. You see Mike Hauser, who made that beautiful picture of our galaxy. Here you see David Wilkinson, and here John Mather. And here the result of this experiment. I got to explain this in a little detail because it's kind of confusing. The thin line is the theory. This is what it ought to look like. The thick line is the measurement, under which is the theory, of course. The other symbols are discrete measurements made by other groups. And you see something that is absolutely gorgeous. A dead close fit of theory and observation. This is the smoking gun. This radiation could not be produced in the universe as it is now. We know that because the universe is transparent. It's not a black body. We know it's transparent because we can see those distant radio galaxies I was describing earlier. This radiation is traveling freely from where? From the early stages of the hot universe. Here it is, tangible evidence. Just like dinosaur footprints convince us those improbable-looking creatures did walk the face of the Earth, so this tells us that our universe did expand from a hot, dense state. What an advance. It's truly amazing. Well, I can't let this moment pass without reminding you that there is a competition in any measurement in science. Here is Herb Gush, who during the time from the mid-70s to 1990 was working on his own experiment, this one to be a rocket rather than satellite experiment, to measure this radiation. It's not a very good picture, but I think you can see this guy exudes confidence. He is a solid person. Here are his two associates in the experiment that worked. Mark Halpern on the left, Ed Wishnow on the right. You can see it's a terrible reproduction, but it's one of my favorite images from astronomy. I just love it. Because, you know, you look at that, I ask myself, if I didn't know these guys had done something great, if I only had this image to judge them by, would this image inspire confidence? I just can't resist another verse. You see that I'm a very poetical person. Another verse about Barbara Fritchie, who you remember during the Revolutionary War saying, "Shoot if you must this old gray head, but spare your country's flag." And then I have in mind Ogden Nash's take on this situation. "I always admired Barbara Fritchie. I bet she scratched when she was itchy." Great science is done by committed, capable people like these two. But first of all, great science is done by people who scratch when they're itchy, like the rest of us. Well, here it is, tangible evidence that our universe is understandable in a way. It has an evolution, it has a history, and a surprising one. It began hot and dense and expanded to the present time, leaving a fossil. Like any other fossil, this one has interesting clues built into it that I will be discussing tomorrow. But I think this is a good place to start winding down, and I've decided that because there are some questions I receive time after time in giving this talk, I thought I would review them now ahead of general discussion. So here is my list of the 4 most frequently asked questions in my experience on this subject. So the first question. So you claim our universe expanded from some dense, hot state. So what was our universe like before the Big Bang? Well, of course, people have worried about this. There are very attractive ideas on what the universe was doing before it was expanding. But the solid part of our subject, where we have the experimental evidence, is in the evolution from the dense state to the present. Don't ask us to do everything. We're going to leave some science for the next generation. The part that is solid is that expansion from high density to the present. So the next question, so can you at least say where this Big Bang happened? Can you point to the place in the sky? Hello? Didn't you see that map of the radio galaxies? Didn't you see how uniform it is? There's no edge that we can see to the universe. The universe is everywhere, and it's expanding everywhere. There's no center. Why do you keep avoiding the term Big Bang? Because it's so misleading. A bang, to me, connotes an event. But I just tried to tell you, we don't have a theory for that event. What happened as the universe started expanding? What we know, and have tested well, I think, as I'll describe in more detail tomorrow, is that the universe has expanded from this dense state, hot, to the present. What is more, a bang connotes a location. It exploded right, there's where the bomb was. But there's no location in the expanding universe. It's everywhere, expanding at almost the same rate everywhere. If you're so smart, this is something I've often asked myself. In the connection of research and cosmology, my answer is we're pretty smart. We've made some striking advances. I've shown you one. I'm going to describe some more tomorrow. We're not all that smart because there are lots of questions you can ask me that I can't answer. Tomorrow I'm going to describe some of these deep puzzles, which I'm going to put a very positive spin on, saying we're leaving lots of work, lots of fascinating research to be done by the next generation. We're not that smart, but we are making progress. Thank you.
Professor Peebles has agreed to respond to questions from the audience. Are there any?
Thank you for the 4 questions, and part of that is some of the data that you have and put in 2-dimensional play comes back and with the red shift indicates that it's 3-dimensional. My question is, has anybody made a model of what the universe was like when those earliest photons first reached us, or on the opposite side, now that they've traveled all those billions of years, where are they now projected to be now when we finally get the information?
This gets complicated, doesn't it?
Yes.
The galaxies are moving away from us as if we were at the center of the Big Bang. Isn't that right? But yet in this theory, if you go to a distant galaxy, you will see the galaxies around you moving away. You'll even see us moving away from you as if you were at the center of the explosion. The central thesis of this first law of cosmology is that the universe is uniform, the same everywhere, aside from local deviations, local clustering. You may say, this radiation that is streaming toward us came from somewhere. Indeed it did. But it wasn't aimed at us. Go to a different place, you'll see radiation hitting you. Wherever you are, the radiation is streaming by. One could ask, where is that radiation going? It's traveling through the universe. It's not being lost. Each photon is conserved, apart from the few that hit dust and get absorbed. they rearrange themselves, keeping uniform or close to uniform in this expanding universe without an edge. I don't know if that's comfort, but the best I can do.
Well, I have a very simple question. I'd like to know, in your opinion, if the universe, like a balloon, is bounded, unbounded and finite, or is it unbounded and infinite?
I'll be discussing some aspects of this tomorrow. The evidence is that the balloon model is a little misleading. The evidence is that space is not curved in the nature of a balloon, but rather flat in our three spatial dimensions. Space-time is curved, to be sure, but a space section is flat, not curved inward or outward. I use the balloon analogy because, to me, it's visual. I can see it, if you see what I mean. But the evidence, as I say, is that space is flat. I can't tell you that space is infinite because the universe is only about 14,000 million years old. During that time, light has traveled a finite distance. We can't see beyond that. We can't check that the universe extends arbitrarily far beyond the section we can see. And in fact, popular ideas about what the universe was doing before it was expanding would project that we're in a section of universe that's enormous but finite, outside of which there's a terrible mess that we won't think about.
Is there any independent evidence aside from redshift that would give a signature showing that the early universe was more compact, more dense, such as, let's say, gamma ray burst? Is there some signature, some empiric evidence to show that with increasing deep time observation, there is a higher compaction of the superclusters and clusters of galaxies?
Yes, excellent question. Give me more evidence. I promise tomorrow to offer some more evidence. The more pieces of evidence we have, of course, the tighter the story, the better the cross-checks, the more believable is the picture. I feel confident now that we have the tangible evidence. It always is indirect, of course. We can't travel in a time machine back in time. We can instead only look at the clues that nature offers us and interpret them and find, once we have an interpretation, whether new clues as they come in fit the interpretation. The more clues that fit, the more confident we are. I'll describe tomorrow some of the clues that convince me that we're on the right track, while at the same time leaving open some very deep puzzles.
You told us some very interesting history about one paper that got hidden in Dutch. Could you tell us a little bit about what happened with Gamov's paper and why people didn't know much about it?
That is another very interesting story. Gamov had many of the ideas of the now standard hot Big Bang, if I may use that phrase, back in the 1940s, including a now well-tested theory for the origin of the light elements, deuterium and helium, including the hot radiation that should be detectable now by instruments we have. That was written at about the same time that Bob Dicke invented the radiometer that I showed you illustrated, and that was capable of detecting that radiation. The two groups never got together. And by the time Bob Dicke in the mid-1960s persuaded David Wilkinson and Peter Roll to build one of his radiometers to look for this radiation, that paper of Gamov, that set of papers of Gamov, had been pretty well lost to sight. When I started working in this field in 1964 approximately, I knew nothing of Gamov. I knew nothing of that early work. I discovered that much of my early work was in fact reinventing Gamov's wheel. We got together. We got the whole story by about 1970, but there was a time of great confusion when we didn't realize what had been done earlier and what hadn't. Maybe you're aware that that left Gamov very bitter. He felt he wasn't thoroughly recognized for his accomplishments, and that might have been so, I hope we got the record straight before his death, though.
The most popular model for the evolution of the universe has it proceeding from a singularity and going through an era of inflation. Another model has a collision of membranes in a hyperspatial matrix. So my first question is, are you going to be discussing that tomorrow? And if you're not, could you briefly discuss it today? My second question is, you seem to be a very optimistic fellow. You seem to be a very optimistic fellow, and the evolution, the rapid evolution of cosmological knowledge over the last 100 years has indeed been a model of optimism in the progress of knowledge. Does the cosmological community feel a dampening of that optimism with the influx of information regarding the possible termination of civilization due to global warming? So I have a technical and a sociological question. Thank you.
I will not discuss inflation or brain collisions as models for what happened before the universe was expanding, described by the theory I've mentioned. That's for another set of lectures. And what is more, it is pretty controversial. These are new ideas, and new ideas always are speculative, controversial, to be checked. The checks are not yet in, to the extent that we have for the idea of a universe that's expanding and cooling. On that point, I was until recently a pretty pessimistic fellow. I was skeptical that we had all of the pieces in place, but I'm going to describe tomorrow why I was driven to accept that we do understand in outline what the universe has been doing since it was dense and hot. As for the future, well, I hope we will devote resources to saving this island universe we live on, the planet Earth. I hope we'll also devote a little time to curiosity and continue to study the large-scale nature of the universe. It has lots of secrets to show us still. I am very optimistic about the prospects for future research in pure science. I'm optimistic about the payoff of some aspects to be determined of pure research in better civilization, if only we'll pay attention. Am I optimistic about the human race? Well, I don't know.
Please join me in thanking Professor Peebles for a very interesting presentation.